Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at a problem with a diffuser, which is the opposite or the inverse of a nozzle, right? Whereas a nozzle, we're trying to convert flow energy, internal energy, into kinetic energy. Here it's the other way around. We want to convert the kinetic energy into pressure, flow energy, or internal energy. So the idea is to really stop the air that's coming in so that it comes into a compressor with already a higher pressure and a steadier flow, less chances of having turbulent flow, more laminar flow, all those good things that assist our compressor. So the problem statement reads for this question here, air at 0.83 bar and 5 degrees Celsius enters the diffuser of a jet engine. The air decelerates in the diffuser to a negligible velocity, while its pressure increases to 1.27 bar. This process can be assumed to be adiabatic and reversible. That is, according to the relation, pressure times volume to the K is a constant, where K is the ratio between C sub P and C sub V. Calculate the final temperature of the air and hence the velocity as it enters the diffuser. Okay, so we need to find two things here. We want to find the temperature, or the temperature of the outlet, whatever you think is easier to relate, and the velocity, 1, or the velocity of the inlet. Try to keep consistent. There you go. Okay, what is important? Well, we have the pressure in bar. Okay, so this is the same thing as 83 kilopascals, and over here 127 kilopascals. We have the temperature in Celsius, so we want to convert this into Kelvin because we're dealing with air, and I shouldn't have skipped this, but this is also relevant because air can be approximated to an ideal gas. So relevant that it's 5 degrees Celsius because we're going to go ahead and convert that to 278 Kelvin so that we can use the ideal gas relationships. What else? The diffuser has the purpose of decreasing the velocity, and indeed it decreases it to a negligible velocity. So this is saying, you can assume velocity to be 0 at the outlet of the diffuser. The process can be assumed adiabatic, so no heat. Let's put it over here, no heat entering or leaving, and reversible. So the delta E, or SGen I should say, entropy generated is 0. And it follows this idea here of P times V equals constant. All right, so this is what we have. Pressure and temperature on the inlet, only the pressure on the outlet. Note that we have this state completely defined in terms of thermodynamics. We can grab everything we need over here. On this side here, we still need one extra piece of information. So what is the deal with these? It's always the same idea, right? We're going to grab, if we need extra pieces of information, we're going to grab off of this state. With this, we're going to find a second thermodynamic property for the second state. With that, we have the whole thing defined, and we can, with that, happily calculate anything we want, including the velocity on this side, which is going to be found through energy balance, first law. Okay, so note that we have on the first state, we have everything but the volume, and we can calculate the volume if you want using PV equals nRT, the relationship. And what we can do is, because of this relationship, we can find a second thermodynamic property that is specific volume for the second state, right? Just relating this property here. So that is goodness, because that means we can define the second state. So let's start with, so my game plan here will be, first, I'll find specific volume of state 1, or the inlet state. Then I'll use PV to the K to find out what specific volume for 2. Once I have specific volume for 2, I can use the PV equals nRT relationship to find what is T2. That's one of the things we're looking for. Once I have all of this in place, what I can do is do energy balance. Let's do delta E equals 0, I can use this to be able to calculate the velocity 1. And I'm going to do volume 1, volume 2, just to not to confuse it with the velocity. All right, so first things first, we know P times V equals M or nRT. That means that P specific volume equals RT. And that means that if I want to find the specific volume for inlet, volume for the inlet, volume, all we need to do is take the R and the T and divide that by the pressure, all of which I happen to know. So my R is 0.287. That's a constant R for air, assuming this, we're taking the R for the air. So this is not the general one. This is a specific one for air. The inlet temperature is 278 Kelvin, and the pressure on the inlet is 83 kilopascals. Okay. What happens here, unit-wise, is that we have kilojoules per Kelvin per kilogram multiplied by the Kelvin, and the whole thing divided by kilopascals. So Kelvin and Kelvin, kilo and kilo, and then joules and pascals becomes meters cubed. So this is meters cubed per kilogram. So this equals 0.961 meters cubed per kilogram. Beautiful. Now with this, I can go ahead and relate this property of this specific diffuser to go ahead and calculate, okay, what's the idea? Well, I don't have volume, I have specific volume, but since we know specific volume is just the volume divided by the mass, and since I know that I can derive the whole thing, and we've done this before, so I'm going to do it fairly quickly. Derive here in respect to time, derive here in respect to time. This does not care about the derivation, so we're going to get mass flow rate, volume flow rate with the specific volume. So specific volume times mass flow rate equals the volume flow rate. And because this is true, and because the continuity is true, that is, there's no mass accumulating in state 1 and 2. And again, just to be super clear, we have videos talking about continuity equation, all these things here in the channel. So if you're not sure what I'm talking about, you can check those out. Because of all those things are true, I can go ahead and happily say that P1 specific volume 1 to the 1.4 equals P2 specific volume 2 to the 1.4. And it's a subtle change, but it's a change that requires these things to be true so that I can do. So just checking if they are. And what I'm really after here is specific volume 2 to the 1.4, which is equal to P1 to specific volume 1 to the 1.4 divided by P2. And we know all this, so this is easy for us to calculate now. This is 83 kilopascals. 83. And here I could have put this in bars because as long as they're the same unit, that would be okay. But here I'm just keeping on the SI, and then this is the one we found out to be 961 to the 1.4. Okay, this number wise is 0.6184, and that has to be equal to P V2 to the 1.4. So if I want V2, and I do want V2, what I want to do is take the root to the 1.4 of that 0.684. This turns out to be 0.709. And that we can keep the units. To keep the units, all right, just to be sure, what we're doing here is kilopascals divided by kilopascals divided by the unit of the specific volume to the 1.4. Okay, so these guys go away, and we're left with this guy here. And then when we take the root, we take the 1.4, so we eliminate this, and we're left only with what's inside. So that comes here. And remember that this was important because this is the second, where is it? The second property, second thermodynamic property for this state here. I didn't have a second one until just now. And now I do. So now I have this one completely defined too, which is great because now what I can do is if I want to find the temperature, so I've done this, then I got this, and now that I can define the temperature, which is what I'm looking for.